Let's look at another example of optimizing a scenario using this new concept of Lagrange multipliers. So, as it's pretty easy to read it on the screen, we want the volume of this cylinder to be 10 cubic centimeters. So how do we design the cylinder so the surface area is a minimum? You could look at it as what's the least amount of materials would we use to build the cylinder, but we want the volume to be fixed at 10 cubic centimeters. So in order to do this problem, we need to have a function that we're minimizing, as well as some sort of a constraint or fixed concept. We know that the volume is going to be fixed, so that will end up being our constraint here. So let's do some geometry. The volume of the cylinder would be the area of the circular base multiplied by the height, and the surface area would be the area of the two circles, the top and the bottom of the cylinder, plus the area of the side of the cylinder. And if you were to unfold the side of the cylinder, it would be a rectangle. The length would be the circumference, the height would be the height of the cylinder itself. I'm not going to go over that in more detail, but I wanted to at least highlight it so somebody could go back and play that in slow motion and try to figure out what it is I just said. Now, what's the actual question put in sort of a mathy type terms? Well, the actual question is to minimize this surface area function. Variables would be the radius of the circle and the height of the cylinder, and the constraint would be the volume that is equal to 10. The volume that's equal to 10. So this is the actual question that gets us pretty close to being able to follow the formula. So, moving forward, our goal is to find the dimensions of, so the radius and the height. Here we go. All right. So the quote-unquote formula is that the gradient of this multivariable function will be equal to the gradient of this multivariable function multiplied by some scalar or constant, lambda. Now, let's start doing some calculus calculations. The gradient would be the vector. If we take the partial derivative with respect to r, so 2 times 2 is 4 pi r to the first power, plus, if r is the variable, that will be 2 pi h. And then the second component of this vector will be the derivative of this function with respect to h. So that would make this term's derivative 0. And if h is the variable here, that would just give us 2 times pi multiplied by r. Okay, so that's the gradient of the function we're trying to minimize. We want that to be equal to lambda multiplied by the vector that is made by taking the gradient of this function. So if r is the variable, 2 pi rh, 2 pi rh, and if h is the variable, pi r squared would be the partial derivative. Alright, so it could be said that this is an equation to be solved. What it really is part of a system of equations to be solved. We would want the x components to be equal to each other and the y components to be equal to each other. So that gives us 4 pi r plus 2 pi h should be equal to 2 pi rh multiplied by lambda 2 pi r h multiplied by lambda, and 2 pi r will be equal to pi r squared multiplied by lambda. So that's two equations, but if you observe carefully, we have r, h, and lambda. We have three variables. So finding a unique solution with two equations and three variables is, we'll call that problematic. You're going to really dive deep into that subject when you take linear algebra, if you have not yet. But it turns out that I actually have a third equation to use, and that third equation is my constraint. I also know that pi r squared h is equal to 10. I now have three equations, three unknowns, and as messy as it might look, it's actually not too bad to solve. The answer may not be pretty, but solving for the dimensions won't be too bad. Now, if you are in my class and you're one of my students, I always attack by removing lambda from the scene first. I need the dimensions of the cylinder, which are r and h. So I'm going to get rid of lambda as my unwanted guess first off. Now, I can do that a couple different ways. I'm actually going to begin with this equation because there are fewer terms and just solve it for lambda. I can slide this up now here. Lambda would be equal to 2 pi r over pi r squared, and that means that lambda would be equal to 2 over r. Alright, so whatever r is, if I knew r, 2 over r would be the scalar, the constant lambda. I'm going to now substitute that into the lambda that is up here in the first equation and see what we can do with that mess. I'm using arrows to at least give you a map to follow later on. Let's see. 4 pi r plus 2 pi h equals 2 pi r h, and lambda would be 2 over r. Alright, 2 divided by r. Right. R reduces, and let's just smooth this paper northwards a little bit here. 4 pi r plus 2 pi h equals, see, 4 pi r divided by r reduces to 1 h. I have like terms. If I subtract 2 pi h from both sides, I will get 4 pi r equals 2 pi h. Remember, pause and slow down for little algebra computations like that. And I don't know, what can I do here? Let's solve for what h is equal to. H would be equal to 4 pi r divided by 2 pi. That's going to be equal to 2r. That's not an answer. That's a statement that tells us that the height is double the radius in a cylinder to minimize the surface area for a volume of 10. Remember, I said that there were three equations to work with, and let me slide this here. Our third equation now comes into play. And we'll take this piece of information and use it as well. So, h is 2r. So pi r squared h is 10, but I just discovered that h is equal to 2r. And that means that I have 2 pi r cubed equals 10, r cubed equals 10 over 2 pi, which would be 5 divided by pi. So that means the radius of this particular cylinder must be the cube root of 5 divided by pi. Now I get kind of excited at a point like this. My excitement here is kind of related to what it's like being a student, where you have that feeling like you're finally almost finished. What was the question? Well, we needed the dimensions. I need the radius and I need the height. Well, I now know that the radius is the cube root of 5 divided by pi. What's the height? Well, the height is equal to just double whatever the radius is. And the height would be 2 multiplied by the cube root of 5 divided by pi. And if you don't have a calculator, that's as good a spot as any to finish. Those would be our dimensions that were requested at the beginning. If you do a quick check for the volume of the cylinder, which is a very good idea to do, pi r squared multiplied by height, you will find that you get 10 as an answer. But I'm going to leave that little calculation for you because I don't want to take all of your fun away. Okay, until next time.